Hey everyone, and welcome. Today we're tackling a neat little problem called smallest number with all set bits. It's a fun one that touches on binary numbers and pattern recognition. Let's break it down together. So here's the goal. We're given a positive number, let's call it n. We need to find the smallest possible number, let's call that x. That meets two conditions. First, x has to be greater than or equal to our input n. Second, the binary representation of x must be made up of only ones. No zeros allowed. Let's make sure we're totally clear on that second rule, all set bits. This just means that when you write the number out in binary, it's a string of ones. For example, the number 3 is 11 in binary, so that's a valid number for us. The number 7 is 111 in binary, also valid. But the number 5, which is 101, is not valid because it has a 0. Our goal is to find the first number in this valid sequence that's at least as big as our input. Okay, let's walk through an example. Say our input n is 5. First, we ask, is 5 itself a valid answer? Well, 5 in binary is 101. Since it has a 0, it's not valid. So we need to find the next valid number. Let's list out our special all ones numbers. The first is 1, which is smaller than 5. The next is 3, still smaller than 5. The next one is 7. Is 7 greater than or equal to 5? Yes, it is. Since we're looking for the smallest such number, 7 is our answer. Let's try one more, with n equals 10. 10 in binary is 1010. Again, not valid. So we go to our list of special numbers. 1 is too small, 3 is too small, 7 is too small. What comes after 7? Well, a number with 4 ones, 1111, which is 15. Is 15 greater than or equal to 10? Yep, so 15 is our answer. Just a quick heads up. We'll be walking through the solution using Python, but don't worry if that's not your main language. I'll be showing the full code for other popular languages like Java, C++, and JavaScript towards the end of the video. So how do we find these special numbers without checking every single integer? If we look at the sequence we've been building, 1, 3, 7, 15, you might spot a pattern. To get from one number to the next, you can just multiply by 2 and add 1. This simple formula is the key to solving the problem efficiently. We can just keep applying this rule to generate the next number in our sequence until we find one that's big enough. Okay, we've talked about the big picture and the logic. Now let's see what this looks like as actual code. I'll put the full solution up on the screen first. And don't worry, after that, we'll walk through it together. Alright, here's the Python code. It's really short and sweet, which is great. As you can see, it directly uses the pattern we just talked about. Let's break it down line by line. First, we initialize a variable, x, to 1. This is our starting point, the very first number made of all ones. Then, we start a loop that continues as long as our generated number x is less than the input n. Inside the loop, we do exactly what we discussed. We update x by multiplying it by 2 and adding 1. This generates the next number in our sequence, like going from 3 to 7. Once x finally becomes greater than or equal to n, the loop stops, and we just return x. That's it. So how efficient is this? The time complexity is big O of log n. This is because our number x roughly doubles with each step of the loop. The number of times you can double something before it reaches n is related to the logarithm of n. It's very fast. For space, we only use one extra variable, x, to store our current number. This means the space complexity is big O of 1, or constant space, which is as good as it gets. Alright, that covers the main solution in Python. As promised, for those of you who code in other languages, I'm about to show the full solutions for Java, C++, and JavaScript. I won't be breaking these down, so just pause the video on your language of choice to check it out. Alright, as promised, here is the full solution in Java. You can pause the video here to take a closer look at the implementation. Notice we use a long for x just to be safe and avoid any potential overflow as it grows. Next up, here is the C++ version of the solution. Again, feel free to pause and review the code. Similar to the Java version, we use a long type for our variable x to handle large numbers safely. And finally, here is the solution in JavaScript. Hopefully seeing it in a few different languages helps solidify the concepts. So let's wrap it up. The key to this problem was first understanding what a number with all set bits really means. Once we listed a few of them out, we could spot that simple mathematical pattern, multiply by 2, and add 1. Using this pattern, let us build a really simple and efficient solution that jumps directly from one valid number to the next, instead of slowly checking every single integer. Alright, before we jump into the other languages, I want to quickly show you a personal project I built to solve a problem that always drove me crazy. It's an app called My Daily To-Do. My biggest frustration with every other to-do app was retyping the same things every single day. Go to the gym, review code, work on the daily Leetcode problem. You know the drill. So, I built my app around one simple but powerful idea: separating your routine tasks from your one-off tasks. Routine tasks, marked with the little refresh icon, automatically reset for the next day. One-off tasks, like ship new feature, get the little puff of smoke icon, and they disappear for good once you're done. This small change turns a dumb checklist into a smart scheduler. If that sounds useful, you can try it right now on the web. The link is in the description. And one more thing I want to make super clear. Right now, as a thank you for being an early supporter, the app is 100% free. There are no ads and no subscriptions whatsoever. This means you get access to everything, including really powerful features like presets, which let you save entire task lists and load them with a single tap. Now down the road, creating new presets will likely become part of a premium plan to help support the channel. But, and this is the important part, any presets you create now, while it's all free, are yours to keep and use forever. So it's the perfect time to check it out on the web, play with all the features, and build out your perfect setup at no cost. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more Leetcode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the Playlist tab and find a playlist that fits your goals. Also, if you're looking for even more Leetcode problems beyond the daily challenge, I've started a second channel called Leetcode Unlocked. It's where I'll be posting solutions to a ton of other problems, so if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this Leetcode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. If you want to support the channel, a few people have asked how I plan my solutions. I'm a big fan of sketching out the logic and data structures on a tablet before I code. It really helps. I've put affiliate links in the description to the tablet I use and a few other good options. Using those links doesn't cost you anything extra but really helps me out. Or, if you're feeling generous, there's always the Boba Fund. Keep coding, and I'll catch you in the next one.